that this top surface right over here, S3, it is a subset of the plane Z. Z is equal to 1 minus x. It's a subset that's kind of above the unit circle in the xy plane, or kind of the subset that intersects with our cylinder and kind of chops it. So let's think about x and y's first. So x, let's think about it in terms of polar coordinates, because that's probably the easiest way to think about it. I'm going to redraw kind of a top view. So I'm going to redraw a top view. So that is my y-axis, and this is my x-axis. And the x's and y's can take on any value. They essentially have to fill the unit circle. So if you were to kind of project this top surface down onto the xy plane, you would get this orange surface, that bottom surface, which looked like this. It was essentially the unit circle, just like that. Let me draw it a little bit neater than that. I can do a better job. So let me draw the unit circle as neatly as I can. So there's my unit circle. And so we can have one parameter. We can have one parameter that essentially says how far around the unit circle we're going. So that would be our angle. And let's use theta, because that's, well, just for fun. We haven't used theta as a parameter yet. That's theta. But if we had x's and y's as just a function of theta and we had a fixed radius, that would essentially just give us the points on the outside of the unit circle. But we need to be able to have all of the x, y's that are outside and inside the unit circle. So we actually have to have two parameters. We need to not only vary this angle, but we also need to vary the radius. So we would want to trace out the outside of that unit circle, and maybe we'd want to shorten it a little bit, and then trace it out again, and then shorten it some more, and then trace it out again. And so you want to actually have a variable radius as well. And so you could have how far out you're going. You could call that r. So for example, if r is fixed and you change your ranges of theta, then you would essentially get all of those points right over there. And you would do that for all of the r's, and from r0 all the way to r1, and you would essentially fill up the entire unit circle. And so let's do that. So r is going to go between 0 and 1. R is going to be between 0 and 1. And our theta is going to go all the way around. So our theta is going to go between 0 and 2 pi. Let me write this down. I wrote 0 instead of theta. Our theta is going to be greater than or equal to 0, less than or equal to 2 pi. And now we're ready to parameterize it. X of r and theta is going to be equal to, so whatever r is, it's going to be r cosine theta. So x is going to be r cosine theta. Y is going to be r sine theta. That's going to be the y value, r sine theta. And now z is essentially just a function of x. Z is going to be equal to 1 minus x, but x is just r cosine theta. So there you have it. We have our parameterization of this surface right over here. The x's and y's can take all the values of the unit circle, but then the z is up here based on a function of, well, really on a function of x. It's 1 minus x. And so that will give us all of the possible points right over here on the surface. You pick an x and y, and then the z is going to pop us right here someplace on that surface. And we can write it as a position vector function. Instead of calling that position vector function r, since we've already used r for radius, I will call it, I don't know, let's call it, I'm just going to pick a random letter here. Let's call it p for position vector function. And so p, our surface p, we can write it as, actually no, I'll just call it surface 3. So surface 3, I'll do it in that same purple color too, just so we know we're talking about this. Surface 3 as a position vector function, as a function of theta and r. Maybe I'll write r and theta, because that's how I think of things. R and theta is going to be equal to r cosine theta I plus r sine of theta j plus 1 minus r cosine theta. Need to get some real estate here. 1 minus r cosine of theta k. 1 minus r cosine of theta k. And now we are ready to start doing all of the business of evaluating the actual surface integral. So the first thing we need to do is take the cross product of this, the partial of this with respect to r, and the partial of this with respect to theta. And so let's just get down to business. Let's take the cross product. And so we have our I unit vector, we have our j unit vector, And we have our k unit vector. And this might get a little bit involved, but we'll try our best to just work through it. Give myself a little bit more space. And so the partial of this with respect to r. So let's take the partial of this with respect to r. I'll do it in blue. The partial of this with respect to r. The partial of this with respect to r is just cosine theta I. So this is just cosine theta. I said I was going to do it in blue, and that's not blue. So this is going to be cosine theta. The partial of this with respect to r is sine theta. And the partial of this term right over here with respect to r is negative cosine theta.